Excuse me. Are people here? I hope people are here. Not early? No, it's not. Hi, Lauren. Lauren, could you post a thing in your WhatsApp chat to remind people about this? That'd be super. Hi, Isaiah. Okay, Isaiah, thank you. Perfect. All righty. Isaiah's here and Lauren is here. Oh, hi, Lillian. Okay, people are slowly showing up. Everybody got their coffee? You got water. That's healthy. I like that. That's good. Healthy. Healthier than coffee. Although I like coffee a lot. It stunts growth. Yeah, I think that's a myth, Isaiah, but yeah. I mean, if you haven't noticed, I'm a pretty large person in every direction. So this coffee has not stunted my growth. But then again, maybe if I didn't drink coffee, I'd be like 7 feet tall. That could be. And like 600 pounds or something, possibly. Maybe. Not sure. Okay, so let me see. We have 3 of you here. Is that okay, Isaiah? But I know Isaiah wants to get real tall for the basketball thing, so that's cool. Still only 3. That's kind of a little bit sad. Maybe they're forgetting or sleeping through it. I'm not sure. I am not sure. But either way, we'll start doing a little physics, and then those guys can maybe watch the video later. That might be a good idea. So we haven't seen each other in a while, about 2 weeks, 3 weeks, I think, actually, because of all the weirdness with Abitur and all that stuff. So the last couple of weeks was pretty packed full. But I do still want to make sure we finish up on our topic of electric circuits. And you guys have learned quite a bit, and at the same time probably forgotten quite a bit because we haven't seen each other for a while. So let's do a quick little circuit and then talk about power. We're talking about power and circuits. That's our topic. So just for fun, yeah, I have a weird idea of fun. Let's draw a little circuit on the board. We have a power supply, and we have 2 resistors in sequence. There we go. And we're going to say that this is a 3 ohm resistor, and this is a 6 ohm resistor, and this is 18 volts. We've got an 18 volt battery connected to 2 resistors, a 3 ohm resistor and a 6 ohm resistor. Okay, and because we love physics so much, let's talk about how things are related. Just a reminder, this is the total voltage difference here, potential difference here. We would normally call this resistor 1 is 3 ohms, and resistor 2 is 2 ohms. And there's, hi, Matthias. So we got a couple questions here. First of those being, how much current is flowing in our circuit that we have here? We've got 18 volts hooked up to 3 ohms and 6 ohms in series, okay? And we'll put up here our Idiotendreieck that everybody loves about the situation. which represents Ohm's law, which is delta V I R. That's Ohm's law. There we go. Hi, Isaac. Good. So we've got a little circuit. We're practicing this, seeing how much current is flowing. So let's talk about the current in this circuit. We have 18 volts applied to these two resistors. How much current is flowing? Well, first of all, let's figure out how to rearrange this to get current. Just a reminder, current is I, then resistance is R, and delta V we generally call the voltage difference or potential difference. Is delta V. So those are the three things that we're interested in. Okay, and just to remind you how to do the Idiotendreieck, which you guys are all big fans of. Right? We're interested in I, so to find I, we cover it up and see, oh, okay, I is equal to delta V over R. And of course, this means the total applies to the total divided by the total. When you're doing Ohm's law, it's always important to remember what part of the circuit are we using this for. And in our case, we're using it for the whole circuit. We're thinking about this as the total potential difference. We're talking about the total current flowing through both resistors, and then the total resistance of these two resistors together. So it's pretty clear what delta V total is, right? Because it says it right here, it's 18 volts. But what is the total resistance in this case? Just write it in the chat. Nine ohms is right, Isaac, because this is a series circuit. Yes, I am series. Okay, this is a series circuit. There we go. And for a series circuit, it is true that the total resistance is equal to the sum of the individual resistors. Simply adding them together, if the resistors are after each other in series, you can just add them together. So for our case, 3 ohms plus 6 ohms equals 9 ohms. Okay, so now we can go over here and get our total current because we know delta V total and we know R total. We know both of these. Doink, doink. So good. 9's good. So here we go. So I total equals 18 volts divided by 9 ohms. You guys are all quick with that. What's that? Just type it in the chat to feel smart and to show that you're actually still not passed out on your keyboard. There we go. Good job. And Lauren, what's the unit on that? Good, good, good. So we can call those amps or just A, and we can write it like this. Technically, they're called amperes, but we can also just abbreviate that as amps. 2 amps, 2 amperes, 2A is correct. Okay, let's make sure we keep reviewing a little bit just to make sure we still have, everything okay. We'd like to know, we'd like to know if we hooked up a voltmeter here. Call this voltmeter 1. Okay, so I'm going to hook up a voltmeter and actually measure the voltage across resistor 1. Okay? Amperes is correct, Lauren. Good job. So we're measuring the voltage across, or the potential difference across resistor 1. How big is that? How big is the potential difference across this? How big should it be? Okay? If you guys think you have the answer, Type it in the chat. What do you think it is? Oh, let's do it in green. That's a good idea. Delta V1 equals. Okay, I'm guessing you guys don't know. Now, so earlier on, I'll just help you along a little bit. Earlier on, I said when you're using Ohm's law, it's really important to focus on the subscripts. Okay, so for the total current, we needed to use the total potential difference divided by the total resistance. So now that we're only looking at one of the resistors to find the potential difference across one of the resistors, we need to make sure that we use Ohm's law, but only for resistor 1. So looking at our Idiotendreieck up here, we want to know delta V, so we cover it up, and delta V is therefore I times R. Okay, and delta V1 is therefore equal to I1, the current through resistor 1, times the resistance of resistor 1. Okay, so here's our situation there. So the first question for us is, how big is the current that flows through the first resistor? Isaac, you're on the right track. Correct. So how much current is flowing through the first resistor? And let me just ask you this. Is the current flowing through the first resistor the same current as the current flowing through the second resistor? And is it the same current flowing in total through the circuit? Or does the current change? Does the current change in the circuit? So if we were to draw in kind of say, this is I total, this is I1, this is I2, and this is I exit, or something like that. Are all of those currents the same, or are they different? Stays the same. Correct, Lauren. So this is one of those key things. Remember, this is where we're putting the analogy in our head of a ski resort. Yeah, exactly. So you're dropped off with your friends up here at the top of the ski slopes. Then you decide to ski down the first slope, and then you ski down the second slope, and then you get back on here. But the same amount of people are dropped off here as go through this, down this run, and then go down this run. There's no way for them to go anywhere else because they have to follow this path. So the current's the same. So in this case, that's 2 amps. Good. So, and then we just have to multiply that by the resistance of resistor 1. And that, of course, is how big? How big is resistor 1? Shows it right there. 3 ohms. Okay. Good. So we get 6 volts. Okay. And now let's do the same process for our second resistor here. And I'm going to do that one in red to get a nice little contrast, hopefully, on the projection. Good, good, good. So we're going to do over here and say go here. Here's our, we're going to hook up a second voltmeter, V2, and connect it over across the second resistor. And our question is now, how big is delta V2? How big is delta V2? Let's scooch this down just a little bit so it shows up. So we're interested in delta V2. Okay, good. So same thing applies. So you guys do this one by yourself and come up with your answer. And if you have the answer for delta V2, just go ahead and type it in. What's the voltage drop across the second resistor? 12 volts is correct. So let's just kind of review the current. Oh, okay, that's okay. That's Liam, yes? All caps, is that you? Yeah, got it. Good. So it's 12 volts. Okay, let's take a look. We've got, again, the current, I2 is 2 amps. We got this resistance of R2, which is 6 ohms, which is 12 volts. Okay, super. Now, You could have, nice job, Lillian, correct. So we could have also looked at our other two answers. What do you mean other two answers? Well, we knew already delta V total was 18 volts. And we also knew that delta V1 was 6 volts. So what did that tell us? That told us that the ski lift lifted us up 1,800 meters, 18 volts. Okay, I'm just using the meters to make the analogy work for you. So the ski lift lifted you up 1,800 meters, and then you went down your first run, and the first run dropped you 600 meters. So you had gone up 1,800, you went down 600, and then if I ask you how much more do you go down on the second run to get back to the bottom of the ski lift, then you can say, oh, we were lifted up 1,800, we dropped down 600, so the amount we dropped down on the second one would have to be 1,200 in order to get to the total of 1,800. And the name for that law is Kirchhoff's loop rule. We talked about that. The idea that the amount you get pushed up is equal to the amount you travel back down when you go through a loop, which makes sense because at this point, you come back to that same point, you're back at the same altitude, so plus 18 minus 6 minus 12 is equal to 0 because you're at the same elevation. Okay, and that's Kirchhoff's loop rule. Okay, cool. Okay, good. 18 minus 6 is 12. Super. I'm going deliberately slow to make sure you get this, and I hope I'm not too boring. I'm aiming for boring, just slightly boring, not incredibly boring. So if you've passed out on your keyboard and are drooling on your computer, I am so sorry. Now, we have well, we don't have to. What do we really have to do? But we'd like to talk also about power. Okay, how much power is generated here? So we have that one equation up here. We talked about that. That's Ohm's law. We also have a power relationship, and the power relationship, we'll put that down here. Okay, so we have a power relationship that the power created or used up in a circuit is I times that's crap. Sorry. Delta V. P is I times delta V. So if we want to know the power that's generated in each of the circuit elements, so for example, we want to know P1. Okay, we need to take again I1 delta V1, and we find out how much power is produced or released in the form of heat or light or energy that your cell phone uses in that case. So we just have to plug in I1 and delta V1, and off we go. Okay, we have those numbers, so I'm just going to leave that there for a second and ask you to do that. We know I1, we know delta V1, we can find the power output of resistor 1. And when you have the answer, just type it in the chat. So good job, Liam, even including the units. Okay, so Liam punched in 12 watts. So I1, still the same current. The current stays the same in the whole circuit. It's 2 amperes. We have 6 volts is the voltage drop across the first resistor. And that, of course, altogether is 12 watts. Benjamin, you got the door? She's here to pick up the keys that are hanging there. All right, cool. So it's 12 watts. Good job. Now, question is, how much power in the second one? Power 2. And that, of course, would be I2 delta V2. So you guys find this one now. Okay? 24 watts. There we go. You guys are rocking it. Okay. So we got 2 amps times 12 volts is equal to 24 watts or 24 joules per second. And of course, it should be true that if we look at the total power, right, that works too. So the total power should be the total current times the total volt potential difference. So let's take a look. We have a total power of equal to the total current. Well, that's still 2 amperes. Good. And of course, the total voltage, the potential difference is 18 volts. Well, that's 36 watts, which is good because that means that this thing is working out. If the first resistor is producing, consuming, radiating, whatever it is doing there, 12 watts, and the second one is radiating off 24 watts, like if these are 2 light bulbs, for example, then of course the total needs to be 36 watts. Okay, cool. Does that make sense? Okay, good. So I think we kind of looked carefully at that, and that's really, really good. That's important work. And at this point, we're going to switch over and take a look at a parallel circuit to kind of remind ourselves of how that works. And we're going to specifically take the same numbers. I hope I've never done this specific circuit with you, have I? I hope not. That would be kind of lame. But okay, so we're going to look at the same numbers we had here. So we had delta V equals 18 volts. And we're going to look at this like this. We're going to take those 2 resistors we had, the same ones, and hook them up next to each other. A little bit of a different setup, okay? So we here have again R1, and R1 was 3 ohms, good. Well, that's too small, hard to see. So, okay, 3 ohms. And here's R2, and R2 is 6 ohms. All right. That is correct. Okay, let's take a look. And looking at this problem, this is a parallel circuit. Am I serious? No, I'm not serious. This is a parallel circuit. Ha! That's good, Jeff. Good stuff, good stuff, good stuff. Okay, so the parallel circuit. Okay, so here we go, a parallel circuit, and we're looking at this situation and want to know, the same things we knew last time. So last time we were talking about, I'm actually going to start the question a little bit differently here. So we're going to say, okay, well, what is delta V2 and what is delta V1? Okay, there are 2 questions. How big are delta V1 and delta V2? And just a reminder about the equations that hold. The equations holding are still the same. We still have our 2 Idiotendreiecke. So there's one. This is delta V I R. And the other one that we might need at some point, P I delta V. So, good. 18 volts is correct, Lauren. They are both the same. Nice job, team. So the idea being, you get off your ski lift here. It's lifted you up 1,800 meters. And then you have a choice of going down one run or the other, but they both get you to the bottom of the ski lift. So the total drop is 1,800 meters for our analogy, or 18 volts. So here it's true that delta V total is equal to delta V1 is equal to delta V2 is equal to 18 volts. So that's really important. A little way for students to remember this sometimes is that in parallel circuits, the voltage difference or the potential difference is the same, whereas for a series circuit, yes, I'm serious, in a series circuit, the current's the same that travels through. Series, current's the same. Parallel circuit, the potential difference is the same. So we have 18 volts traveling, not traveling through, 18 volts applied to this one and 18 volts applied to that one, which means, of course, that we can find the current. The current in this case is not constant. We have a total current up here, or in our analogy, we thought about this as you and your friends being dropped off at the top of the hill, and then some of the students deciding to go this way because they're better skiers, worse skiers, whatevs. But it splits. I1 and I2 are the currents that split off I total. Another way of putting that is to say I total is equal to I1 plus I2. We call that also Kirchhoff's junction rule because at this junction, the currents split. So this is kind of referring to this junction because at that point, the red point right there, you make a decision whether to go this way or the other way. And the same thing happens for the current, although of course the current doesn't have free will, doesn't make a decision. It's based on the physics, which direction it goes. Okay, so let's find the individual currents I1 and I2, and then the power, and I think it's going to be a little tight for us to get that done, but let's see how much we can get done. I'm going to go a little faster now because I do want to at least finish the review. We didn't get much past this, but because we haven't seen each other in 3 weeks, I think that's okay because we're still doing important learning, I think. So of course, I1, looking at the Idiotengleichung, I is delta V over R. So I1 is delta V1 over R1. Good. We found out that the potential is 18 volts. Divide that by R1 is 3 ohms. So we have 6 amperes for our current flowing through this resistor. The red side has 6 amps. Good. Excellent. And we can do the same thing for I2. We're going to kind of squeeze it up here a little bit. I2 is equal to delta V2. Okay, we'll just write it in right away. That's 18 volts, therefore, divided by its resistance, which is 6 ohms, which is 3 amps. Okay, so I'm going to just stop there for a second, not the class, but look at that for a minute. So we see that here I2 is 6 ohms, R2 was 6 ohms, and it got 3 amps. Okay, and the 3 ohm resistor got 6 amps. So we see that in a parallel circuit, the smaller resistor has the bigger current. Okay, so the bigger current here, whoopsie, I wanted to use red and I got confused with the colors here. So this is crapperoo, there we go. The I1, the smaller resistor, has the bigger current, and the bigger resistor has the smaller current. And what I wanted to point out for you guys is that that's the opposite effect from the series circuit. I don't know if you noticed it, but we have a situation where the smaller resistor, well, not the opposite, but here the current was the same, and that has a profound effect on the power output. For this situation, we had a power output that ended up being the smaller resistor had 12 watts and the bigger resistor had 24 watts. Yeah, that was the result we had down here. So for a series circuit, the smaller resistor has less power than the bigger resistor. Okay, and in this situation, because they both have the same voltage, but the bigger resistor has less current, it has less power, and the smaller resistor has more power. So it's a flipped effect, where in a parallel circuit, the smaller resistor has more power, and I'm going to leave that to you as homework, okay, to find here P1, and to find, I should have done that in red, P2, and compare to what happens in a series circuit, and you'll find that effect that I just described. And we're at our 30-minute mark, and I didn't want to go over that. So it was good seeing you guys today. I'm planning on having another class next week around the same time. And make sure you get all your stuff in. If you have anything missing, I already messaged you guys. I'm looking to make sure I score everything. And then grades are due on Wednesday, but of course, officially grades are not in the book until June 22nd. So do watch out with that for other classes too, because that's when the grade conferences are. So you do want to make sure you have your ducks in a row. Okay, so get your ducks in a row, and good seeing you guys. I'll see you guys next week. Bye. Oh, Lauren, I called it homework, meaning I'm not going to collect this, but I didn't have time to finish it. So if you want to do it, you'll get to see the effect that I described. But I was going deliberately slow to make sure that we were able to review. Okay, good. All right, good seeing everybody. Bye bye.